Okay, this video is to teach you about what's called an oxidation-reduction reaction. Oxidation-reduction reaction is a mouthful, so we're going to shorten that down to what we call redox reactions. Redox reactions take the first few letters from reduction and oxidation, switch them around, and make it something that we can say rather quickly. Redox reactions, much better than oxidation-reduction reaction. You start sounding rather robotic or rather Cajun. Now, do not mistake redox for Red Bull. RedOx, it's not RedOx, it's redox, reduction oxidation reactions, not Red Bull. So do not mistake those, although we'll call Red Bull our official sponsor of today's video. So, what's an oxidation-reduction reaction? Here's what it's not. An oxidation-reduction reaction is not a new kind of reaction compared to synthesis, decomposition, single replacement, double replacement, combustion reactions, all those 5 that we've talked about already. This isn't like the 6th type or something. Essentially, redox reactions kind of cover all of those reaction types, with the exception maybe of double replacement reactions where we don't see this happening. But synthesis, decomposition, single replacement, and combustion could all be considered to be redox reactions because they meet the qualifications to be redox. And redox are quite common. So what the heck is a redox reaction? Well, basically the idea is that a redox reaction would be any in which we see electrons being rearranged or reassigned in such a way that elements have a different oxidation number at the beginning than they have at the end. Now, how do you tell the difference between oxidation, reduction, and how do you assign these numbers? Good news, you've already done a lot of the number assigning. So the only thing that we have to talk about is how to tell the difference between being reduced and being oxidized. So here it is. An atom is reduced when it gains electrons. Now that might seem a little opposite. Reducing seems like I'm losing but not gaining. No, reducing means I'm gaining electrons because when you gain electrons, your charge is reduced. Your charge becomes more negative or goes down or is reduced. When you gain electrons, you take on negative particles, and that means your charge is going down and being reduced. On the flip side, oxidation is when you lose electrons, and when you do that, you become more positive in charge. So oxidation means you're losing electrons and your charge is increasing or becoming more positive. So reduction is the gain of electrons, oxidation is loss of electrons. Reduction is gain, oxidation is loss. I want you to remember that phrase or those 2 phrases to help you keep track of this if you feel like you're going to lose track of which is which. Reduction is gain of electrons, oxidation is loss of electrons. A good friend of mine who teaches chemistry taught me this mnemonic, oil rig. If you can remember the mnemonic oil rig, it'll help you to remember the idea that oxidation is loss. That's what this abbreviation would be for. Oxidation is loss of electrons, and reduction is gain. If you can remember oil rig, you've got it. Reduction is gain. Again, both of these phrases meaning of electrons. So when we talk about oil rig as our mnemonic, that might help you to keep track of what's going on with those electrons when we talk about oxidation reduction, because it's really easy for folks to get these mixed around. Okay? But oxidation is loss, reduction is gain of electrons. Remember that if it helps. To determine which atoms are oxidized or reduced, we look at every atom's oxidation number throughout the equation. You've already actually been doing this a lot because we did a lot of oxidation number assignment when we did synthesis and decomposition reactions. So if you've already been through those with us, then you know just how to do this without even knowing that you know. What you'll do is go through and give every atom an oxidation number and see who changed. Important thing to remember, we haven't seen a lot of this yet, but we want to see it now and remember it. When you have an uncombined element in an equation, a plain old element, a metal, a nonmetal, a metalloid, anybody, before they've joined into a compound, their oxidation number essentially is treated as 0. They come in neutral, they haven't lost or gained any electrons yet, and so protons equal electrons and their charge is neutral. You'll see some of these in the examples that I'm about to do with you. But uncombined elements, whether they're in the products or the reactants, will be neutral and the charge will come in at 0. So what does that look like? Let's look at the examples on the sheet that you should have picked up in class, either today or previously. And if you don't have this sheet, then follow along with us and copy these examples down so that you've got them to go off of as examples of oxidation reduction. So what's going on in this first example? This is about one of the simplest synthesis reactions we could find. Hydrogen and oxygen joining together to make water. So when hydrogen and oxygen combine, as we see them doing here, 2 elements become a compound. 2 elements, 2 plain elements. And remember, just a moment ago we said uncombined elements are neutral and have an oxidation number of 0. So don't make this any tougher than it needs to be. Hydrogen has an oxidation number of 0 before it gets in a compound, and so does the oxygen have an oxidation number of 0. Now, when they get in the compound, they take on the charge that we're used to them having. And typically in compounds, 99 times out of 100, hydrogen's oxidation number, or charge sometimes, will be +1. And oxygen's oxidation number will be -2. Now there are exceptions on these, but they're quite rare for both oxygen and hydrogen. So if this works, go with it, because it'll be right almost all the time. So we've got every atom assigned, the hydrogens, the oxygens, and at the end, the hydrogen and the oxygen in the water. What's happened? What's changed? Who's been reduced? Who's been oxidized? Remember, reduction or being reduced means that your charge has gone down, and you've done that by gaining electrons. Well, whose charge has gone down here? We can see that the oxygen, if I read my equation from left to right, and I always want to follow the arrow and read from left to right, the oxygen has gone from 0 to -2. We'd consider that to be reduced. From 0 to -2. It's going downward in charge. So to fill in my table, I would say oxygen, the element oxygen is being reduced, and it's going from a 0 to a -2. Now I'm going to draw mine in here with a little slant to them, so it kind of looks like we can kind of remind ourselves that reduction means the charge is going down. And I can see it sort of almost going down like a slide here from 0 down to -2 when the element's oxidation number is being reduced. On the flip side, an element has to be oxidized. So who's being oxidized? Well, there's only one other choice here, and usually that means that's the element being oxidized. So who is that? Well, it's hydrogen. Hydrogen's going from 0 to +1. Not a big change, but it is a change. And that's considered oxidation because it's going up. Its oxidation number is being increased because those hydrogens are essentially losing one electron, at least the electrons that they're being assigned. So who's being oxidized? Hydrogen is going from an oxidation number of 0 up to an oxidation number of +1. And as usual, I don't care if you write +1 or 1+. I do them with the charges after the numbers. Typically, it's up to you. But again, to show that hydrogen's oxidation number is being increased from 0 up to 1, that's oxidation. And we just like that, we would recognize this as a redox reaction. We've assigned who's been reduced, whose charge was going down, and whose charge was going up. In this case, that was the hydrogen. It's going to be the same on every example on this page, but let's do a couple more so I can show you a couple of other things. On number 3 in our examples, and again, if you don't have the sheet, then just jot it down. We've got mercury oxide becoming mercury and oxygen. So this is a decomposition reaction. And again, we've got two uncombined elements here, mercury and oxygen, in the product side. So these are raw, plain old, everyday elemental mercury and elemental oxygen. So we'll give those charges or oxidation numbers of 0. They have their protons and electrons equal and neutral. But in the compound over here, they're not neutral. They're not zeros. Again, what holds them together is the fact that one of them is positive and one of them is negative. So we need to assign those charges. Well, we know oxygen typically in a compound, unless it absolutely doesn't work, oxygen's charge is -2. And if oxygen is -2, in order to balance this compound out, hopefully you recognize that the mercury would have to be +2. I've got one atom of each. If the oxygen is -2, the mercury would have to be +2 to balance that out. Well, who's changing then? Well, who's being reduced? And remember, reduced means my charge is going down. My charge is becoming more negative or less positive, depending on how you look at it. So as mercury is being reduced from 2+ to 0, we want to show that change and say mercury is the one that's going down from an oxidation number of 2+ in the reactant side to an oxidation number of 0 in the product side. That's reduction. And on the flip side, oxygen, as you might expect, its oxidation number is going from -2 up to a 0. So oxygen is my element being oxidized from -2 up to 0. And again, you don't have to draw these arrows in. I just like to show them to kind of remind us that that's the way this charge is changing. Now, in our example here, I want to point out that being reduced means your oxidation number is going down, becoming more negative, but it doesn't mean it has to end up negative. In this example, an element started out, mercury, at +2 and went down, but didn't end up negative, ended at 0. Likewise, oxygen over here started negative and went up, became more positive without actually ending positive. So it doesn't mean you have to end up with a positive number in order to be oxidized or a negative number to be reduced. You just have to have gone down to be reduced and gone up to be oxidized. So keep in mind that it's not quite as limiting as we might sometimes think. Now, this is number 5. On number 5, we have a single replacement reaction. And number 5, we have, like on the previous one, some elements that are by themselves. We have sodium and we have hydrogen. Both of those are elements in this equation, so we can call them neutral zero oxidation numbers. Water, well, we've seen water before. That was in the first one we did. And in that one, oxygen was +1, or rather -2, and hydrogen was +1. And that's what we'd expect. And in sodium hydroxide, there are no surprises either. Sodium in a compound tends to take on a +1 charge, oxygen a -2, and hydrogen a +1. And when we put all those together, +1, and -2, sodium hydroxide is neutral, just like we'd expect. Comes in at 0. So which element is being reduced? Well, if I look around in this equation, I might notice hydrogens are going from 0, or rather, I'm sorry, hydrogens are going from +1 to +1. That's no change. And that's true for some of the hydrogens, but we've also got some hydrogens that are going from +1 to 0. See, these hydrogens going from the water to the hydrogen gas are seeing a change, and that's reduction from +1 down to 0. So we kind of have to look around a little bit and notice that not all the hydrogens are doing the same thing, and that's pretty common. So be on the lookout for some atoms of a particular element doing one thing and others doing something else altogether. Which element's being oxidized? Well, we've got oxygens that are going from -2 on the left to -2 on the right. So there's no change there. We could sort of consider the oxygen as spectators of a sort. But the ones that are changing and being oxidized are those sodiums. And there's sodium going from 0 to +1. That's an oxidation. The charge is increasing. So sodium being oxidized from an initial charge of 0 up to a charge at the end of +1. So in this case, sodium oxidized, hydrogen reduced, and essentially the oxygens aren't changing at all. Some of the hydrogens aren't changing either. And that's common. As we get into bigger and bigger equations, there'll be more elements than we can sort of label as reduced and oxidized, and typically the ones we'll look at in our class. You'll only see one element reduced and one oxidized. Maybe a few other elements that don't do anything. Now, I'm going to talk to you next about redox agents, but for the time being, let's cut this video off there, and we'll pick up on redox agents on the next one, explain what those are all about. For now, your assignment on that first page is to finish up the equations that we didn't go through as examples and see how many you can handle. Most of them are pretty straightforward, pretty simple. I think you'll be able to handle them. There are a couple on the practice page that I'm assigning this first time around that are a little sticky and tricky. Give them a try, see what you can come up with. But I would say that 17 or 18 out of 20 on there are pretty easy. So do your best with those, and we'll see those the next time I see you in class.